everybody, welcome back. So this is chapter 5, and this is in a new packet because the format from the chapter 5 I gave you is so much different that I thought it'd be worth our while just to have a new packet for this. So if by chance you don't have a packet because the packets didn't make it here in time after I requested for them to be copied, then we just are working on a piece of paper. So we are going back to linear and exponential functions, all right? We got our learning targets, as you can see, and let's go ahead and just get started. So when you open up your packet or you're just on that piece of paper, we are on what's page 2, just at the very beginning. So our goal in this section is, given a set of data, so a bunch of points on our graph, we want to see the function of best fit, and then we want to write its equation. And the two functions we are working with are linear functions, all right, which has a constant rate of change. Remember, that's the amount that you add or subtract each time. Or you have an exponential function, which increases or decreases by this ever-changing amount. So remember, when it increases or decreases, it's because we're multiplying by the same amount. So let's just remind ourselves of what those two equations look like. So in a linear function, and a function instead of y, remember we just use that f of x. So a linear function is, I'm going to write it a little bit backwards, but you start with some beginning amount, b is by itself, and then you'll either add or subtract some amount each time, over and over and over. So we're used to seeing y equals mx plus b, so let's just put that over here on the side so you remember y equals mx plus b. Then we have our exponential equation. So I'm going to put that down here in green. And we also, and this time I'll start with y instead of f of x. So we also start with the beginning amount. And then that is multiplied to some amount in parentheses. G is called the growth factor. And this is the beginning amount, and this is what we multiply by each time. And we see our shape get bigger or smaller. And this time our x is a little exponent. So these should look familiar to you, all right? And let's just take a look, refresh our memory of how we figure out, we know which one's which. So in order for us to figure out if it's linear or exponential, your x's should be going up by ones in this pattern. And what we want to do is focus on the y's and see how to go from one y to the next, to the next, to the next. So we're going to determine whether the following tables represent a linear or exponential function. So I always like to start with linear. So the ones that are linear, I'm actually going to go through those first. So again, my x's are going up by ones, but when I look at my y's, this is going down. And so what I want to see, is it going down by the same amount each time? And actually, I don't know why I started with this one. Let's start with this one, example 1. So my x's are going up by 1, and I go from 7 to 14 to 28 to 56 to 112. So as I was saying, I like to see if it's linear. So, and since it's getting bigger, what I want to see is, are they adding the same amount each time? So they're not adding the same amount each time. To get from 7 to 14, I add 7. To get from 14 to 28, I add 14. To get from 28 to 56, I add a different amount. So then I want to see, well, maybe they're multiplying. So what do they multiply to get from here to here, or here to here, or here to here, or here to here? So I can see 7 times 2 gets me to 14, or 14 times 2 gets me to 28, 28 times 2. So the fact that each time they're multiplying by 2 says it's exponential. Now, if you're having trouble seeing what they're multiplying by, remember, you can take one amount and divide it by the previous amount to get your g, because this 2 is g. So if you can't see what they're multiplying by, take a number and divide it by the value in front. So if I divide those, I get 2. Or I could take 28 and I could divide it by the amount in front of it, and that's also 2. Or I could take 14 and divide it by 7 and get 2. So this is exponential. Now, in the past, we could write the equation because we can see our y-intercept. Remember, all y-intercepts are when x, or in this case, t is 0. And we could write the equation. So our function is c of t, and we have a y-intercept of 7, and then we can put in parentheses our g to the x power. So this one is exponential. So let's just write a little exponential. All right, let's take a look at this one. So here, the x's are going up by 1, which is what I want. And I want to look, this is going down. So again, I always like to check with linear. So since it's going down, are they subtracting the same amount? So 20 take away 17 is 3, 17 subtract 3 is 4, 14 subtract 3 is 11. So what I notice each time is that they are subtracting 3. And then that becomes your m value. And then you can write your equation because you can identify your y-intercept. And it goes y equals m x plus b. And I'm using x and y because that's what they use. And in our next one, from 21 to 17 to 12 to 10 to 7, so this one's also going down. So here, from 21 to 17, I have to subtract 4. From 17 to 12, I have to subtract 5. From 12 to 10, I have to subtract 2. So it's definitely not linear. So let's see if it's exponential. So what do they divide, or what do they multiply this to get to this? I have no idea. So what I would do is see if I can figure out what g is, and I would take some amount, and I would divide it by the amount in front. Or maybe I would try to take 10 and divide it by 12, or 17 and divide it by 21. So I definitely want to check this out a couple of times, because what I should see is when I divide these three, here's my calculator, and the first time I get 0.7. So according to that, that's g. But when I take 10 and divide it by 12, I don't get 0.7. And 17 divided by 21, well, that's not the same amount either. So as it turns out, this isn't linear or exponential. So this was what we would just say neither. Now, as it turns out, these points might actually look close to being linear, or they might look close to being exponential, and that's what we're going to start to look at. What if it's not perfectly exponential, or, which I didn't write up here, perfectly linear? So here we go. Several real world scenarios follow linear or exponential patterns, but they don't fit it perfectly. So you're not going to have a perfect line or a perfect curve. So what we can do, though, is we call this an equation of best fit. And had we all had calculators, and this wasn't COVID, we would actually do all of this on your calculator. But what we do is we run something called a regression. And what we want to do is the regression takes your data and puts it and it graphs it for you. And what we want to do is we want to see, is there a line of best fit, or is there a curve of best fit? Could this look like a line, or could this look exponential? Okay, so as it turns out, this data looks very linear. So, and then the calculator would help us come up with an equation for it, where I have this set of data, and this is that exponential shape. So remember, linear overall can go uphill, or they can go downhill, but it won't be perfect. And exponential can kind of look like a capital L, or it can look like a capital J, capital L, kind of, but there's a curve to it. It's not like a sharp piece. And then again, what the calculator could have done, and I realize this is really small, is it would come up with the equation for us. So what we want to do first is just take a look. Does the data look linear or exponential? So this one, determine if you should run a linear regression, an exponential regression, or neither. So on this one, I definitely see a curve. So I would say this is exponential. So what's missing from that curve is this flat part over here, but I definitely can envision it. So I want to, even if I don't see it all, could it be there? So I would run an exponential regression. And a regression, again, just one more time, is just something on the calculator that you do. And then it would come up with an equation that tries to match those points. This is looking more linear, in my opinion, so I'm going to write a linear regression, and I'm abbreviating regression. And I think this also looks exponential because there's that curve, more like this. Okay, so the point is, once you get those points, your data, on a piece of graph paper, does it look linear or does it look exponential? And if it looks either one, we can let the calculator come up with an equation for that. All right, moving on to page 3. So, when your calculator runs a regression, it attempts to model the relationship between the two variables by fitting either a linear or an exponential equation to the data. So what we're not going to do is actually have the calculator do that. We're just going to show you what the calculator would do. So that's the big difference between my Chapter 5 and how we've changed Chapter 5, is that we would actually go through all of that with the calculator. And it's not to say that we won't, but right now we're just going to look at the data. So what we do, the following table gives the average heights of children ages 1 to 10. So you can see their age in years. If you notice, it is going up by ones. And the thing about this is it actually doesn't have to go up by ones when we're using the graphing calculator to come up with that data. When I look at the height, I notice, whoops, I think this is a typo, it should be 103. The data goes up, then it goes back down, then it goes up, and it keeps going up. So what happens is this data has been graphed, looks like this, okay? And then I ran this feature on the calculator, which I will show you at some point, but I'm just not going to show you today. And it would come up with this. And if you notice, this is very similar to y equals mx plus b. Why they don't use m and why they use a, it's just something that the calculator does. But what I can see right now is I can see what a's value is, which is m, and I can see b, which is the number that's by itself. And I would just write those equations in here. So what we're going to do is, here's the scatter plot. The calculator came up with this, and we're going to write this equation of best fit. So we're just going to fill y equals, and we are going to go thousandths every time. That's 3 numbers behind the decimal. So in for a, we're going to leave this as 6.630. I don't need to round up. Plus b, and I'm going to go 3 decimals back, and that 3 says it can just stay 533. And there's our equation. And so now this table actually kind of becomes obsolete. It's not something that I need anymore. I'm going to use my equation to answer questions. I'm not going to use my table anymore to answer questions. So what we want to do is we want to use the line, this equation, to predict the height of a 12-year-old child. So remember, x is the age and y is the height. So let's just remind ourselves up here. So if you notice, I couldn't even use the table if I wanted to because it stops at 10. So I'm just going to go to my equation and put a 12 in. And then because of the numbers, I'm going to let the calculator do the work. So in for x goes 12. Depending on your calculator, if you're using your phone, you would definitely want to follow the order of operations. And I would multiply those two first. So you can't see my calculator, but I am doing that. And that becomes 79.56 plus the 71.533. So again, I'm just typing this into my calculator as I follow the order of operations, and I get 151.093. And then predicting the height, I would want to label this in, it is in centimeters. So somebody who's 12 years old is about 151 centimeters tall. Now, if a child measures 184 centimeters tall, then according to this model, not up here, how old are they? Now, 184, again, that's not even on here, so I couldn't even guess their age. I know they're going to probably be older than 10. But since this is the height, remember that's going to go in for y. And I'm just putting everything in place. And then we just go about solving for x, but because the numbers have such crazy decimals, I would just use my calculator. So first, to get x alone, is I'm going to move this number. Okay, so I'm doing that on my calculator. And then I have 112 point, this is, again, you can't see my calculator, but that's what's on here. And now to get x alone, I'm going to divide by this number, so I'm doing that on my calculator. And when I'm done, my x is 16.963. So approximate how old they are. Approximating, I would say that they're about 17 years old. Okay? And think about how your answer fits into the data that is given to you. As I said, I knew they were supposed to be older than 10, which they are. So if I got like 3, a 3-year-old's not going to be that high. All right, let's take a look at this one. So a science measures a 50-gram sample of radioactive material over 5 weeks. Her results are shown below. So again, X is going to be X is going to be weeks, and Y is going to be the weight in grams. So we've got our data. Okay, if you notice, it goes down, down, down. It keeps going down. So when I put this data in, though, there's a slight curve to it. So that's where I would allow my calculator to run what's called an exponential regression. So I would put all this data in, and notice, though, they don't use the letters that we typically use. So we use B and G. They use A and B. So Y, it's just the way the calculator is set. So we're just going to fill the numbers in. So in for Y is going to be A, and again, I'm going to go 3 decimals behind. And then what should be with the exponent in parentheses is this number. So again, I'm going to go 3 decimals behind. Now, this time when I go 3 decimals behind, see that 8? That's going to make the 2 round up to a 3. So it's going to become 0.833 to the x power. So there's my equation, okay? All right, now we're going to use the curve of best fit. So we're going to use this, and we're going to approximate what is the approximate weight of the radioactive material at week 7. So since that's the week that I know, that's going to be X. And so I'm just going to go to my paper, write down what I'm about to type into my calculator. And for this one, it's very important that you follow the order of operations if you are going to be using your phone. So this is multiplying to this, which has an exponent. And so I should do the exponent first. So I need to take 0.833 to the 7th power, which I'll show you. So your exponent button looks like this. So I type in I'll put it in parentheses just like they do, 0.833, close those parentheses, hit that, and then I'll put in 7. So just rewriting where I am, Y equals the 46.222. I'm just going to write down some of the decimals here. And then I would just multiply those. And just what I would do is just hit times on my calculator, because I don't want it round my decimal. I want to use this whole decimal. And I would take this times my 46.222. And then I can get what Y is. So Y is, and again, I'm going to round to 3 decimals. 86. So it says 863, but again, that 6 is going to turn the 3 into a 4. So 864. And then I will label my answer as grams. All right? And if you think about it, you know, if 6 and 7 are up here, week 6 and 7, and this is going down, my answer should be less than this 20 because it's getting smaller. All right?